So in the morning we heard how big data and real-time decision making can help us do better science in the field of astronomy. So now we're going to switch gears completely and talk about how real-time decision making can not only help us do better science, I think, in seismology, but also save lives, perhaps. So there's an added imperative here. And the first speaker will be Richard Allen from Berkeley.
Great, thank you. So sorry I wasn't here this morning. So I feel a little bit an unfair advantage in not really knowing the audience too well, but I instead will just throw it back over to you to stop while I've been talking to my mic on. To stop me and ask kind of whatever questions you have about the material I'm going to cover. We're going to sort of have an afternoon talking about earthquakes. And we're doing this in 2 installments. So first of all, I'm going to try and give you an overview of what I think is by far the most interesting aspect of earthquakes, which is earthquake early warning. And sort of what is the purpose of this, what are the goals, try and give you sort of a basic overview of how we do this, what are the sort of fundamental steps that we need to go through when it comes to dealing with large amounts of data. And then after the break, Chinkai, who's one of the graduate students, a very senior graduate student, I might say, in my group, and who is responsible for what's the most exciting aspect of what we're doing right now, I think, which is building a global seismic network using smartphones, using the smartphones in your pocket. And so I'm going to give an overview of that project, but he's going to really talk about some of the nitty-gritty and get into the details of how that works. We figured that might be the kind of material that would be good fodder for this group. So that's kind of the game plan. So say please stop either me or Chinkai at any point, and we'll be happy to go off in some other direction if that's what would be useful. Okay, so I'm going to give this sort of overview talk. So a warning when you need it, earthquakes, smartphones, and streaming data. Two project names, which I realize are confusing for many people, but you're going to fully understand the difference between the two by the time I'm done. One is Shake Alert and one is MyShake. And the difference between these two is really critical, in my opinion. Shake Alert uses traditional seismic networks. It's a proven technology, and we're working very rapidly towards having a public early warning system using Shake Alert. MyShake is a research project. It's not a proven technology, but we're very excited about the potential that MyShake might have. Okay, so why would a warning be useful? Well, just to kind of set the stage a little bit, right now here in California, everybody is more than aware of how much improvement is needed in our warning capabilities generally, in any sense for natural hazard type of events. This is an image from the fires in Northern California. There was, for those of you who weren't in the state at the time, it was a real issue. These fires broke out in the middle of the night. There was widespread failure in warning people about these firestorms that were just burning through areas just north of here, and so there was a number of fatalities as a result of that. And that then, of course, led more recently to the mudslides, mudslides being due to fires in Southern California in the fall as well. And again, there was an issue with alerting, and we saw that the alerting systems that we have failed. And again, the failure here is in actually getting the warning out to people. And of course, we're going to be talking about how you generate warnings. But this all fits into the same question of how do you gather real-time continuous data, process it in a way that's useful, and then use it to provide warnings to people. Getting a little more close to home, this is a picture of an office after the Northridge earthquake in Southern California. This is just to remind people that while we are, for the most part, in buildings that we do not expect are going to collapse, here in California at least, most buildings are not expected to collapse, you can fully expect every building to look like this. Okay? You should be very concerned about these big heavy-duty ceiling tiles that are above your heads if we have an earthquake right now. There's a good chance that they will come down and they'll do serious injury. So even if the building is not going to collapse, Knowing that the earthquake is happening, is about to happen, is enough time to get down between these chairs and actually significantly reduce the impact of the earthquakes. That's the idea of earthquake early warning. This is an image from the Napa Earthquake, so this is very close to home, a couple of years ago now. A very small earthquake. This is just a magnitude 6, okay? In a wood frame building, one of the best types of buildings to be in, and yet still the fireplace like this fell and collapsed and killed somebody. Looking more globally, while we're in good shape when it comes to buildings not collapsing in California, we're not in good shape when it comes to buildings not collapsing in many other earthquake-prone parts of the world. This comes from Nepal. From a couple of years ago again. We're quite used to seeing images like this when we see earthquakes in some parts of the world. Taiwan, even the places where we do have good building codes, Taiwan, still there are significant lapses in terms of how they're enforced, and these collapsed apartment buildings were the result of that. And then finally, it's just amazing how many people need a warning. This guy has got his head in this crack in the road, and no doubt created by the Napa earthquake. In the day after the Napa earthquake, very good chance there'd be an aftershock. Well, there were aftershocks, obviously. Not an insignificant probability there would be an aftershock right now. This is not the situation you want to be in. And while this is kind of amusing, the point here is that when you start to think about the many situations in which you would actually be in harm's way and it would be useful to have a warning, there's many of them. Okay, so, oh, and I have one more, sorry, I forgot about this one. So this comes from Mexico City. This comes from the magnitude 7 earthquake in Mexico City last year, which, as you probably know, did a lot of damage, caused a fair number of fatalities. Mexico City has an early warning system. Okay, so I'm going to show you a video. Mexico has an early warning system, and the siren that you can hear in the background in this video is actually is the early warning system going off. So the early warning siren has already sounded when this video starts. Sorry, we couldn't figure out the audio, so I have to go low key.
Este edificio se movió horrible, horrible, tronó horrible. Que se salgan, la pared se rompió. Que se salgan, te va a caer, te va a caer. Dios mío, Dios mío, Dios mío, Dios mío, Dios mío, Dios mío.
So this is again to make the point that there can be significant time available when it comes to having a warning. Sorry. Even though this actual warning, the sirens only went off when the shaking had actually started in Mexico City, but the buildings themselves didn't collapse for many tens of seconds after the shaking had started. So again, the point is that there can be significant amount of warning. When I say significant, I'm talking about tens of seconds, potentially up to a minute or so worth of warning. So that's what we're talking about getting here. So how's that possible? Well, I'm going to illustrate that with this cartoon animation, but it's showing the biggest earthquake that we have to worry about here in the San Francisco Bay Area. This is a magnitude 8 earthquake on the San Andreas Fault. It's starting up here at the northern end. We're, of course, down here. It's going to rupture all the way. This is the rupture frontier, the broad brown line. It's going to come all the way down the San Andreas Fault. That's what makes it a magnitude 8. The circles represent the energy that's radiating out from the fault. The yellow are the P waves. They travel fastest, but they don't contain that much energy. So they usually don't do very much damage. There's just kind of a thump. So right about now is when we would know this earthquake was underway. And this is a big earthquake, so we would feel this. We would know that this was an earthquake, but we wouldn't know whether this was just a relatively small, moderate earthquake, a magnitude 4, like the one we had a few weeks ago, or actually just the beginning of a much bigger earthquake. Now, the fact that the shaking would still be going on, this relatively light shaking would still be going on, I would now know this was a big earthquake. You guys may not be quite so sure. But it's not until the S wave arrives, which is the red circle, that you really start to feel the shaking, okay? And it's the S wave energy that does most of the damage. So now this building would really be shaking. We would all know that we were in a really big earthquake. But again, we still would not know the full scale of this event, because in fact, it's not until the S-wave energy from the closest section of the fault arrives that most of the damage is done. So the rupture front is still only reached this far. It's going to come all the way down here, and it's when the rupture passes San Francisco here, and that energy radiates across to us here in Berkeley, that most of the damage actually occurs. So that's still another 20, 30 seconds from now. So this is to illustrate the concept behind early warning. Big earthquakes can have significant amounts of time between when they start and when the damage is done. And so the idea behind earthquake early warning is you use sensors distributed throughout the earthquake-prone region to detect the beginnings of the earthquake, push out a warning to people, and then of course you have to continue to update this information as time proceeds. Yeah?
And the warnings or messages are electronic, so they're way far back.
Exactly. You know, it's sort of the seismic waves, they travel at the speed of sound, and the information travels at the speed of light. It's exactly that kind of concept. And you can see here that we're talking about maybe up to a minute's worth of warning. Okay, so that's the concept. That's why earthquake early warning Okay, so why is it useful? I usually have to make this argument. Maybe I don't need to do that today, but I'm so used to it, I'm just going to make the case. Why is earthquake early warning useful? Well, the first is to reduce the impact, even in California where we have good buildings, to reduce the impact from the injuries that I already talked about. I already talked about the effect of an office building here, but here's some actual numbers. In the Loma Prieta earthquake, which was the last major damaging earthquake in the Bay Area, more than 50% of the injuries were linked to falls. And then in Northridge, more than 50% of injuries were due to non-structural hazards. That's these ceiling lighting fixtures and things like that falling on people. So more than half of the injuries, the point here is more than half of the injuries are due to these kinds of hazards. So if everybody received a few seconds warning, that's the first if, and if everybody then took an appropriate action, so drops, takes cover, and holds on, then you could reduce the number of injuries by about 50%. And that is a significant reduction in the impact of earthquakes. Even in these earthquakes, which were just sort of moderate earthquakes, these were not really big earthquakes by the scale of what we were expecting. Even in these earthquakes, in Northridge at least rather, the total cost of the injuries alone is about $2 to $3 billion.
So the amount of warning time you get depends on the origination of the earthquake. Is it reasonable to say that it originates at one end or the other of the fault, or can it originate anywhere?
Right, so first of all, yes, the amount of warning time is determined by your distance from the epicenter of the earthquake, because we're sort of detecting the epicenter as rapidly as possible, so there's some processing time. But then the amount of warning you have is that processing time minus the travel time of the seismic energy to get to you. So that's right. So the farther you are away, the more warning time you get. It's also worth pointing out, of course, that means that the people at the epicenter are not going to get a warning. So they may get a warning, sort of borderline. Even if they get a warning, it's a fraction of a second warning. So that's unfortunate, because obviously people at the epicenter experience very strong shaking as well. And now I've forgotten the second part of your question.
Do they originate at the ends of the...
Oh, do we know where on the fault the earthquakes rupture? The answer is no. So I chose that example of a magnitude 8 on the San Andreas Fault because it's the one that gives you the maximum amount of warning time. Okay, so if that rupture on the San Andreas Fault initiated, which way we're pointing, right offshore of San Francisco, then San Francisco probably would not get a warning, but we're actually far enough away that we would probably get a warning here, but of a second or two. Again, because we're so close to the epicenter. And we have no basis, scientific basis, for being able to guess where on the fault we're more likely to have an epicenter initiate. We know where they've started in the past, but we've also seen that then in future earthquakes, they tend to start in places that we didn't expect. So sort of equal probability of it starting anywhere on the fault. Okay. So that's individuals. That's how individuals can benefit from early warning, because you prevent these kinds of injuries. But of course, there's also then automated response. Slowing and stopping trains is a really big one. The first automated use of earthquake early warning in the US was actually the BART train system here. They started getting our warnings even when it was a research project. And they use it to automatically slow, and then they can manually stop the trains when there's an earthquake. And they do that because there can be 1,000 people on one of these trains going along at 70 miles an hour on one of these raised tracks. You can imagine why they would want to slow and stop the trains. Other applications, stopping elevators, isolating hazardous machinery, hazardous chemicals, data security, things like that. Okay, so how do you get the warnings? There was a question about getting the warning at the speed of light, essentially, but how do you actually get it to people? And the answer to that is that the vast majority of people, they just want to get the warning on their smartphone. That's the number one way that people want to get the warning. Of course, not everybody has a smartphone, but a very large fraction of society now does have a smartphone. And so what might that look like?
Earthquake, duck cover and hold on, strong shaking expected.
So this is an actual app. We actually have this app. I have it on my phone. And so whenever the system detects an earthquake, it pushes out that alert to your phone. You get that audible message. So what you're seeing is a video of exactly what I would see on or get on my phone. The audible message means that despite the fact it's in my pocket, I can hear it. At least some of the time I can hear it. And then you could see that the app itself, it gives you a countdown and also the expected intensity of shaking, which is fairly straightforward to calculate once you know the location and the magnitude of the earthquake. So that's the concept, is you push the warning out to people using this, but also, of course, you would want to push it out in as many ways as you can and in as many ways as people want. We also have an app that you can run in the same way on your desktop computer, and it pops up and makes a very offensive noise to get your attention, counts down, things like that. But in the long run, you can imagine that these would be sort of, the goal here is, while these have been built specially for this, we want this to just become embedded in the technology around us. And so it could be, the alerts could come out through your home security system, through the office PA system, and things like that. Yeah?
Just a week or so ago, we had this example of a false negative alert with the ballistic missile in Hawaii that got pushed out to everybody's smartphone. I mean, what are the dangers of those sorts of false alerts? And has your system encountered them?
Absolutely, we've encountered them. So let me be very clear, we will always have false alerts. The question is, how many false alerts are we going to have? Okay. What are the impacts? So that's the important question when it comes to, so right now we're actually in the process of moving towards a public rollout, a limited public rollout later this year. And so the discussion is all about who should have access. And how do you roll this out slowly so we can sort of pilot it without getting people and pushing it out to everybody and getting ourselves into these kinds of situations. Part of the reason the BART train system was such an early adopter is because they could automatically slow and stop the trains. They wait 30 seconds, they see if anything's going on, and if it is a false alert, they just start the trains up. And if you're local or not, but if you ride on BART trains do that all the time. So nobody will even know that there's been a false alert. So you want to start with situations where the cost of a false alert is minimal. Okay? And then as you build confidence in the system and as you build accuracy in the system, then you start to expand the number of applications that you have. Yeah.
Is there more generally prior work in this? I'm thinking of seatbelts on the light on the airplane.
Right.
Or in, say, petrochemical industry, the more successful. Are there domains large which might involve the general public to a certain extent that work successfully?
Yeah, I actually don't know the answer to that question. One would hope that there is some prior art out there, but I actually don't know. I don't know what there is. I mean, I think that one of the other pieces that sort of links these two questions, I think, is that I think a lot of people are much more tolerant of having false alerts than we might immediately think. And the reason I think that is after this Mexico City earthquake, a team of us went to Mexico to try and fill in this gap as to what is the public response to warnings as opposed to a seismologist's response to the warnings. And give you a whole separate lecture on this, which obviously I'm not going to do, but they actually had they've had a system in place. It did do something. You saw a video, the sirens are going off, so it's not like it's not performing, but there are all kinds of limitations to it. They had several false alerts in the run-up to that significant earthquake. When the significant earthquake happened, they actually only sounded the alarm after the shaking had started, because it was actually right beneath, or kind of right beneath the city. could explain in more detail if you want to afterwards. But then when you go and talk to people, they were more than happy with the system. They understood that the system had its limitations. They understood that there were some false alerts, but they still were very glad that they had the system. So when it comes to the false alerts, their typical response was, well, this is just an opportunity to practice what we would do, to remind ourselves that we live in earthquake country, and what is it that we're supposed to do when there is an earthquake, and then go through that kind of drill. We even talked to the CFO of one company. He tells us it's the equivalent of Trader Joe's, I don't know. But he was ready, he wanted devices in the office buildings and in the supermarkets. And he was quite happy for there to be a false alert every 2 months. Because at a sort of 2 month, I don't know how we got to 2 months, but at a 2 month recurrence interval, to remind people about earthquakes and to practice, he thought losing 30 minutes of work every 2 months in exchange for people being much more aware of earthquakes was a good thing. Okay, any other questions? Let's keep going. Okay, so yes, and then the next point is that the technology exists. So we'll give slight light relief for a couple of minutes. You don't have to believe me the technology exists. Instead, I'm going to have Rachel Maddow tell you the technology exists.
Very interesting. Digital communications travel at the speed of light. Thanks to things like fiber optic cable, we can move information literally in a flash, and that is good, just in the abstract. But that is, it turns out, potentially life-saving. If the information that you are moving at the speed of light is notification that an earthquake is about to happen. Earthquakes happen in a specific place in the ground, right? Earthquakes have an epicenter. But you don't just feel an earthquake at the epicenter. The shuddering waves of motion in the earth from an earthquake, they emanate out from the epicenter of the quake, traveling at the speed of sound. So if you had the kind of motion sensors that detected earthquakes, if you had seismometers along fault lines all over earthquake-prone regions, when there was an earthquake, the seismometers nearest to the epicenter, they could register that an earthquake has happened, right, feel the shake, and then they could send a digital signal at the speed of light, notifying communities nearby that this traveling at the speed of sound tremor, this motion of the earth, is about to arrive. This is not a way of predicting earthquakes before they happen. It's a way of basically warning people that an earthquake has just happened and that they are about to feel its effects. Brace yourself. But this thing works. Scientists at UC Berkeley say that their Shake Alert to Earthquake Early Warning Project, it set off an alert. It did go off this weekend, during this weekend's large quake in Napa, California. It was about to be felt in Berkeley, and this is the alert that told them so. Watch this.
Earthquake, light shaking expected in 3 seconds.
They got a 10-second warning that they were about to feel the quake. And 10 seconds is not much time, right? But this brace yourself warning system, it works thanks to the simple fact that the speed of light is faster than the speed of sound, and earthquakes only move at the speed of sound. With more sensors in more places, they presumably deliver even more warning time. California's hoping to have that bigger system in place in the next few years if they can get it funded and finished. From the LA Times today, once fully developed, the system could give downtown Los Angeles 40 to 50 seconds of warning that the big one was headed from the San Andreas Fault, giving time for elevators to stop at the next floor and open up, for firefighters to open up garage doors, for high-speed trains to slow down to avoid derailment, and for surgeons to take the scalpel out of a patient. Giving your surgeon enough time to get the scalpel out of you before the giant earthquake starts shaking the operating room. That idea of a tectonically shaking scalpel inside your body somewhere, that is something you can never unknow, and I am sorry, but the idea that this warning technology, that it works, that it worked this weekend, in fact. It's not just on a drawing board somewhere, it is in effect, and it could be expanded and is being expanded. That is an excellent thing. They've got a system like this in Japan, they've got it in Mexico and some other places around the globe. California could get their whole statewide system done in a few years. God bless the geeks. They will save us all. Now it's time for the last word with Lawrence O'Donnell. Hi, Lawrence.
Rachel, I just want them to make the earthquake warning voice a little less scary.
Yeah, a little more soothing. Maybe with a little music or something.
Right.
Ding dong.
Yeah.
Thanks, yeah.
Thank you, Rachel.
Yeah.
So I don't know, the thing that sticks in my mind in that was, oh, they could get their system done in a few years. And you can see this comes from just after the Napa earthquake. We're still not there yet. However, we're not there mainly because of funding issues, not because of the science issues. But anyway, so this is a great summary of, this is how earthquake early warning works. This shows that it does work. We actually did issue a warning. That was our proof of concept, the Napa earthquake. We issued a warning for the Napa earthquake. And we have been on a trajectory that is leading to this hopefully limited public rollout later this year because of this event, because of that proof of concept, I guess. So right now, where is the system? The system is processing data from the whole West Coast. So it's using stations, seismic stations from the various networks that monitor earthquake activity up and down the West Coast. I think it's about, actually this says 800, but I think we're up to about 1,000 stations are streaming their data into the system right now. The data is processed at various centers. One of them, of course, is here at Berkeley, and it's sort of shared up and down the West Coast, so it's a single uniform West Coast-wide system. Various groups have been getting the warnings in a sort of prototyping type mode for a year or so, a couple of years perhaps now, including BART, as I mentioned previously. But we are really working towards this limited public rollout. The USGS is the agency that has the statutory authority to issue warnings. And so they're the ones that get to define what it means to do a limited public rollout under pressure from myself and colleagues at Caltech and Washington as to what it should be. But the intent is now that the limited public rollout means pushing the warning out to teachers in schools. And so the idea is to take that app that I showed you a few minutes ago and distribute it to school teachers so that essentially we can get the warning out to schools. There's all kinds of reasons that makes sense that I can go into in a few minutes if you would like. But that's what the status of the Shake Alert project is. So we're about to transition from Shake Alert into MyShake. But before I do that, I thought I should just spend 3 slides, the basics of how does earthquake early warning work, how do you detect earthquakes, how do you locate earthquakes, just so we're all kind of on the same page. Earthquake detection is really simple. It's very basic. We've been doing it in exactly the same way for several decades at this point. Okay? There's 2 stages to it. First of all, you want to trigger when a seismic sensor sees that there's something going on, needless to say. And so here's the classic seismogram where you have 0, 0, 0, 0, 0, big noise, big arrival, and then you have a later arrival. So there are these 2 arrivals, which causes some complexity. But the point is that the expectation here is that you don't have noisy data, that you have just beautiful data with no noise, no signal whatsoever, and then you have the earthquake occurs, you trigger on that P-wave arrival on individual stations. So you start by recognizing that there's an earthquake by seeing that there's some energy arriving at one station, and then you go into stage 2, which is to associate the triggers in time and space. Obviously, if there's an earthquake, you have a whole bunch of seismic stations that are triggering at the same time. So that's all very simple and straightforward. Traditionally, the way that this has been done is using seismic networks. So this is the seismic network, all of the triangles is the seismic network around the San Francisco Bay Area. It's a very dense network compared to most parts of the world. In fact, compared to most of California, as you'll see in a minute. But the point is that the traditional approach, we would wait for tens or even hundreds of seismic stations to detect an earthquake, and then you would declare the earthquake, locate the earthquake, etc. And so the point is that takes minutes, even hours, using kind of the more standard traditional approaches to locating earthquakes. But of course, for earthquake early warning, we want to do this in a fraction of a second or just a few seconds. And so we want to be able to detect seismic arrivals on just even one station. We don't do that, but that would be a nice thing to do. Just 1, 2, 3, or 4 stations, and then locate the earthquake based on that. And that's where the challenge comes in earthquake early warning, is how do you really build enough confidence that you really are detecting an earthquake that rapidly in order to issue the warning. So a couple of examples to show you what some real data actually looks like. So this is actually from the magnitude 4 earthquake. I don't know how many people were here in the Bay Area or in Berkeley on January the 4th, but we had a good shake on January the 4th. It woke me up in the middle of the night. It was a magnitude 4.4 earthquake. The system did detect it, and it did push out a warning. And so the way that's what this map is actually from, the initial alert was generated based on these green triangles. They're the ones that detected the earthquake and were used to push out a warning. This is a great example. It really does look like there's no noise on these seismograms. So very easy to trigger on all of these arrivals. What does it say up here? So the alert was pushed out 4.3 seconds after the origin time of the earthquake. The earthquake was actually at 13 kilometers depth. So that means it takes 2.4 seconds for the energy to get to the surface. So obviously we can't know about it until the energy gets to the surface. And so then it basically took 2 seconds for the system to actually detect the earthquake and push out the alert, which is pretty good. But it means that the area that had already felt the S waves by the time we're pushing out the alert included most of Berkeley. Okay, most of Berkeley and most of Oakland. Over in San Francisco, there was there was a fraction of a second of warning. So that's when it works. Okay, here's an example that didn't work. So now we're looking further north in California. So you can see what I was saying about the Bay Area has lots of stations. The rest of California, or rather this portion of Northern California, does not have very many stations. And that's why we got a false alert. In fact, we've had several false alerts from this part of the state. And I would say that it's driven by the fact that we don't have enough seismic stations in the region. But then here's the data. So you saw what the data from the Berkeley earthquake looked like. This is the data that was associated with this earthquake. And so you can see, and I put this just to kind of give an illustration of some of the challenges with the data. Of course, it's very easy by eye to see what the issues are. This is obviously some kind of data glitch with this step function. I don't know what the blue lines are when it triggers, so I'm not sure what it triggered on in this particular case. And then obviously you just have a huge amount of noise. So the system, even when you have a high quality traditional seismic network, we still run into these challenges of noisy data. And in fact, the most recent version of the algorithms has new approaches to try and recognize. Obviously, it's very easy to distinguish between this kind of signal and this kind of signal, but also to try and remove these kinds of problems as well. But so this is try and give you a flavor of the data that we're using. Okay, so
you're going to say something about locating the earthquake involves some kind of triangulation of signals?
Oh, yeah, sorry. I meant to say that. I can say a little more if you like on this slide. But yes, so the way that the earthquake's located is exactly that. It's a triangulation kind of problem. And so you have the arrival times at a series of stations. We have a velocity model. You don't have to worry about the details of the velocity model. A simple 1D velocity model for the Earth is more than sufficient. And just based on the arrival times, you can then determine the origin time, the location, and the depth of the earthquake. That's right.
So thinking about the problem of the false alerts in the center of California, it seems like, I guess that's partly caused by the fact that the sensors, if the sensors are all equally sensitive, and you have a sparser density of them around that area, then you're more likely to have false alerts.
Right.
It suggests that maybe you want differential accuracy given a fixed budget. Is that something which is possible with the public authorities that are?
So this is, first of all, solution number one is we should have sensors everywhere.
Yeah, clearly, right.
That will always be my number one solution. We're going through a debate about whether, so does the initial rollout, do we just provide alerts in smaller regions where we have denser seismic stations or where we have greater confidence, like basically that would mean the Bay Area, the Los Angeles area, and possibly the Seattle area. But so of course, whenever you run a system like this, you see how it performs, and there are always problems, and then you fix those problems, and then there's more problems. And I think one of the issues that we are going to run into is we're rapidly expanding the network. The networks are now expanding more rapidly than they ever have previously, other than immediately after big damaging earthquakes. That's typically when they build seismic networks. But right now we're expanding the networks without having these big damaging earthquakes. And what I foresee happening is that, in fact, our algorithms that have become over the year very tuned to the network geometries that we have, we're going to start running into problems as the geometries start to change. Even though we're adding more stations, there are all kinds of things like the fraction of seismic stations we want to trigger in a certain region, and these have been, sort of tuned, manually tuned over the years based on what we're seeing. And what I envision is that we're going to start seeing problems with the system just by virtue of putting in more stations. So to me, one of the challenges we're going to have is we need to, in some way, come up with a much more automated way to be assessing the performance of the network as a whole and tune the alerting criteria based on that. So you could, the way you fix the false alert problem in that region is you just wait a little bit longer for more stations to trigger, things like that. But doing that in some sort of automated way rather than on an ad hoc way, which is what we do right now, that's a real challenge for us. We don't know how to do that. Yeah.
Do you take into account any considerations of population structure density?
Well, so when it comes to doing the science part, which is detecting the earthquake, then obviously the population doesn't matter. When it comes to a political decision about where should we issue the warnings, then of course population does matter. So I'm not sure if you were just asking about the former or the latter.
The social.
The social piece. So there's a discussion going on now as to whether we're better off to have the limited public rollout be West Coast wide, even though there are some areas which have better performance than others based on the station density. And are we better off doing that, saying that there are limitations to the system, and then maybe we'll see some failures to the system, and that will be argument as to why the system needs to be improved? Or do you only roll it out in certain areas where you have dense seismic stations and other people are just out of luck? And I don't know the answer to that. Yeah?
An engineering question. As you were mentioning, you were deploying more and more sensors. How much percentage of the cost goes to the sensor themselves, and how much of the cost goes to the communication and data infrastructure?
That's a good question. So over time, I don't have a good answer, so I'm going to give you a half-hearted answer. I apologize in advance. Everybody thinks that the cost of seismic networks is buying the hardware, and that is not true. The cost of the seismic network is running the seismic network, which is the ongoing costs of the telemetry, maintaining the station, having people to monitor the system and catch improvements. So if you look at it like that, then clearly the cost of the instrumentation isn't significant. But it's not insignificant. We still have to buy it. That's the best answer I can give you, I'm afraid. Okay? All right, so let's move on to, so this is the traditional network. We really are going to do warnings this year, I believe. I mean, as in public warnings, limited public warnings this year, I believe. But still the system has issues, and the public's going to have to be ready for some false alerts. Okay, so Shake Alert is coming to the west coast of the US. That is great, and we're very excited about that. But needless to say, there's a whole lot of the rest of the world. As I mentioned, the San Francisco Bay Area has one of the densest seismic networks in the world. We're very fortunate in that sense. Most of the earthquake-prone regions, there's a reason we have the densest network. Maybe that's what that laugh was for. Most of the earthquake-prone regions in the world, which are the red regions on this map, do not have dense seismic stations, dense seismic networks. And so the question is, well, what can we do in the rest of the world? And so that's where MyShake comes in. And MyShake is all about using the smartphones in your pockets. So as you all know, the smartphone in your pocket has an accelerometer in it. It's the same sensor that we use in traditional seismic networks. It's just a whole lot crummier than the one that we put out in the traditional network. So it's a lot more noisy already. Just the sensor itself in the phone is a lot more noisy. But by far the most significant problem is people insist on carrying their phones around with them all day long. Okay? So we have to be able to remove that signal from any actual earthquake signal if we want to make use of the accelerometer in people's smartphones. And that's what we're trying to do with MyShake. That's the piece that Chinkai has figured out how to do. So how does MyShake work? First of all, we want to harness all of these private smartphones, it's not like other, again, I just want to emphasize, we're trying to figure out how to use your smartphone, as opposed to going and buying a whole bunch. I can't tell you how many times people have said to me, why don't you just go and buy a whole bunch of iPhones and you know, deploy them out as sensors? That is an incredibly inefficient way to spend your money to build a seismic network. You can buy much cheaper sensors than smartphones. The whole reason that this will work is that because there are obviously millions and millions of smartphones out there already that we don't have to buy, if we can persuade people to put our app on their phone. And so therein lies the challenge. So we want to make use of private individual smartphones. We want to use the accelerometer in these smartphones and to detect an earthquake. And then when it detects an earthquake, obviously it needs to talk to some kind of back end so that we can recognize exactly where the earthquake is and do real-time analysis. And then, of course, we could potentially provide warning back to the phone operators. We can use it to provide warnings. Our actual objectives with MyShake are much broader than that. We just want to create a global seismic network, and we can do all kinds of things with that data. So that data also then gets stored into an archive that we can use for any kind of research and development. And I'll probably forget to say it later, so let me just say that right now, whenever one of these phones thinks it's experiencing an earthquake, it records 5 minutes worth of data. And we archive that 5 minutes worth of data, although we don't actually need that data for early warning. But the reason I'm talking about this in the context of earthquake early warning is that we think that earthquake early warning is the motivation for why you might put this app on your phone, right? We obviously need a reason for people to put it on their phones. So that's the idea behind MyShake. So the first challenge, as I've already pointed out, is we have to be able to separate out earthquake shaking from all other types of shaking on your phone, which of course is what's happening most of the time. And so the way that we do this is we have a classifier analysis. This is just running on an individual phone. We use 3 characteristics to try and identify whether it's an earthquake, represented by the red dots here, or not an earthquake, the blue dots here. And we find that we use 2-second windows. It's a neural network-based approach. Chinkai can tell you all about it. He's the one that created it. And it's remarkably successful at separating earthquakes from non-earthquakes signals. Based on our tests, we found that it had a 93% success rate on the phone of separating out earthquakes from all of the other motions that you put your phone through. So that's the first step, is we on an individual phone, we see if we think it looks like an earthquake. And then if we do think it's an earthquake, we send that trigger, what we call the trigger, to our back-end server. And the idea is, of course, that then on the back-end server you can confirm that it is an earthquake. So here's an example, some data. This is from the Napa Earthquake again. And so this is just the classifier analysis that's saying it's not an earthquake, not an earthquake, not an earthquake, 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 to illustrate how that works. Again, I'm not sure if I said it, uses 2-second windows of data, and it does this every second. So that does mean that there is some delay in actually detecting that there is an earthquake. And then here's a much longer period of time, 300 seconds of non-earthquake. This is some other human activity, and you can see for the vast majority of the time it recognizes it's not an earthquake, although it does have 2 red dots here. So there were 2 points in time when it did think it looked like an earthquake, which is perhaps not untypical. So that's kind of how it works on the phone. But then once it's recognized on the phone, we then want to use a network detection algorithm to recognize it's actually due an earthquake, because we still get it triggering, individual phones triggering periodically because it's not perfect. So we need to look for a cluster of phones to trigger in order to confirm that there's an earthquake and estimate the location of the earthquake. And the example I'm going to show you actually comes from this Berkeley earthquake just a couple of weeks ago. That was a great test for our system, in that we have all of these phones out. And I'll tell you about that in a moment. And so we could see how it actually performed for this earthquake. And so this is what the MyShake performance would look like. So -1, this is the origin time of the earthquake. 1, 2, the P waves hit the surface. 4 seconds, the red dots are the phones actually detecting the earthquake. And then when you saw the star appear and the magnitude appear, that's when the network detection algorithm confirmed or recognized that there was an earthquake. Yeah.
Maybe this is traipsing into Chicago.
Sure.
So you need a space. You need time and space. Time, I imagine, is a problem. But space. I mean, depending on what mechanism the API is providing. Is that an issue?
I'm not sure I understand the question.
Is spatial position of a smartphone an issue?
Oh, no. So, well, obviously we need to know where the phones are. So when we're doing, I'm still not sure I understand the question. So obviously we're only using data from smartphones where we have the locations of the phones. So yeah, so we do need to know the locations. And then how accurate the locations are is, as in within meters, is not a concern.
Yeah. But there are dropouts.
Yeah, absolutely. But there are dropouts. That's right. Yeah, but I'm going to let you can ask the same question again in an hour. Okay, so I think did this keep running so you could see how it runs a few times? Oh, it looks like it stopped. Let me run it one more time. So hopefully you get a sense. Oh, there we go. It's running. Oh, it stopped. There we go. Of how, so again, the blue are all of the phones that were running at the time of this earthquake. The red are when they triggered, and then the star is when MyShake detected. Now there's a catch, unfortunately. The real-time MyShake system did not detect this earthquake, and it should have. We do not actually understand why it didn't detect. So what I'm showing you is the results of an offline simulation. The triggers are all real, of course. The triggers are the phones actually triggered and sent their trigger message. But for some reason, our back end didn't go and associate these. When we run the same algorithm offline, it works. So what we're showing here is a simulation. It didn't actually happen in real time, but we assume that's due to some technical issue that we haven't managed to figure out just yet, just to be completely honest and transparent. Okay, so that's the idea. As you've already seen, we obviously have rolled out the system because we have all of those phones for the Berkeley earthquake. But this is just to make the point again that we have almost no seismic data in most parts of the world. Again, the example from Nepal, we tried to estimate how many seismic stations there are in Nepal, and it's somewhere between 0 and 10. We really cannot get a good answer on that, but there are 6 million smartphones. So the point is that even in parts of the world where there are no seismic stations, and you might not think there's much seismic infrastructure, or any infrastructure for that matter, the number of smartphones is really quite remarkable. And so if we can really harness these smartphones, we really think we can do this in many, many parts of the world. So we rolled out an app. How many people in the room have an Android phone? Wow, that's better than the usual response for Berkeley. Globally, it's about 50% of people have an Android phone. In Berkeley, it's less than 10%. So that was actually a pretty good response rate. It's only available for Android right now. Yes, we're working on the iPhone version. But if you download the app and you can get it, just go to myshake.berkeley.edu. Right now it's a citizen science project. Okay? So you will not get warnings on your phone. Nobody gets warnings. Right now it's citizen science. You put the app on your phone and you're basically allowing us to use the accelerometer on your phone when you're not doing other things. But of course the intent is that in the future we will be able to start providing warnings. Yeah?
Androids have some sort of gyroscope, but a desktop is more credible for stationary position. And have you thought of a desktop app? Because you'd have to have some sort of hardware.
Yeah.
Possibly USB.
It's kind of interesting. I'm trying to think why we haven't seriously considered that possibility. I guess the reason is that there have been other efforts to use the accelerometers. Actually, there's two parts to the answer. First of all, other people have tried to use the accelerometer in laptop computers, and they've found they've been unsuccessful. People's interest in keeping the app, so people will be interested, so they'll download the app, they'll put it on their computer, but their interest rapidly turns over. And so then when they upgrade their system, whatever, they don't upgrade it, and so it no longer is going to work. There's a second problem. Fewer and fewer laptops actually have accelerometers in them today. So now that this has no accelerometer in it now, as you move to, you don't have a disk, you have a memory chip, whatever you call those things. Thank you. There's no longer a need for an accelerometer. So there actually aren't sensors in the modern laptop computers. So this is the device that has the sensor. These don't.
I mean, I can't resist. I mean, every building has a building automation system, a little computer. California should mandate that everyone have an accelerometer. I mean,
It seems so obvious.
No disagreement here.
Every
But there's still
Wi-Fi access point.
there's still more of these. I mean, I'm not disagreeing with you. Yeah, no. I mean, I actually, the reason I got involved in this project, at least 5 years ago now, was I actually was asked to do a review of seismic networks around the world. And these computer-based networks, people have been trying it. There's a group at Stanford built the Quake Catcher network, a group at Caltech still working on the community seismic networks. They were trying these low-cost types of networks. And so I wrote this review piece, and it was really interesting to me that these low-cost networks were all struggling because they couldn't maintain the network. That's what somebody asked about the cost of running networks. It's not the hardware, it's the manpower to maintain the network over time. And so they were all struggling with that. Plus they were struggling with the fact that people's interest wasn't there. And so that led me to thinking, well, let's go way down, to the poorest quality sensor, which is also the most common sensor in your smartphone. But the other piece is that it is much easier. You can all I have to do to get data from your accelerometer is get you to go to the App Store and download a piece of software. There's no hardware, there's no, it's the system is set up to send the software to your phone and start providing data. And so that's why we started to pursue it. But people keep insisting that there are better places to put accelerometers. I agree. But they haven't done it yet. Yeah.
So I wanted to connect this with your earlier comment about the difficulty of changing topology in the fixed network.
Right.
It seems to me that's a challenge you must have to surmount continuously here. Is there a way to use the solutions you're developing for this problem?
That's a really great question. So I think that the answer is that we have not had enough. So we have not issued any warnings with MyShake. The Berkeley earthquake is the first time that our system should have the real-time system should have detected it, but as I said, it didn't for some reason we don't understand. So I guess my answer is that we have not gotten to the point where the challenge is dealing with a varying topology. The challenge with MyShake is that we don't have enough phones. I haven't yet shown you how many phones we have, but the reason we haven't detected more earthquakes is we don't have enough phones. And so that's the challenge. I guess we haven't gotten to that challenge when it comes to the MyShake problem yet. Interesting though, in terms of using the technology, the way that we're removing some of those false events from Shake Alert is by applying similar kind of techniques to what Chinkai developed for the smartphones in terms of characterizing the arrivals, the P-wave arrivals, in order to throw out some of these false triggers from the traditional seismic network.
Just one small follow-up I was going to suggest is that there's probably lots of interesting ways to incentivize adoption of the app through, so for example, like if you're an insurance provider and people download phones for insurance, provide a small discount if you also contribute.
Yeah. So we've actually talked to the California Earthquake Authority about doing that. So that actually is an ongoing conversation, that there are these various routes. And frankly, this Berkeley earthquake was a turning point for it 2 weeks ago, because it's the first event that we should have detected. Yeah. Up until that point, we were really struggling to show that we had to an end-to-end system. We still can't prove we have an end-to-end system, but I have no problem now sitting up and saying we now know we have all of the pieces in place. Okay, so I still haven't. The punchline here, of course, is how many phones have actually have the app running, but you kind of already know the answer at this point. So this already is by far the largest seismic network in the world. Since we launched in February of 2016, so almost 2 years now. Not quite, almost 300,000 people have actually downloaded the app. It's truly a global network. Today, so of course there was a lot of media and excitement when we launched it, so it wasn't that surprising that we had this big download. It literally became a global network over the weekend. We launched it on a Friday. It was a very stressful weekend. But by Monday, we had a global network with, I think, about 80,000 users. 2 years later, we still have 20,000 active users. So we're actually quite pleased with that. And on any particular day, about 7,000 phones actually send data to our back end. So it's a pretty sizable network. It really is a global network. There are some gaps. China is a big gap, and that's because China doesn't have Google. So there's still some of these kinds of technical challenges that we will have to work our way through if we wanted to do a truly global network.
China has Google, but it's just not allowed.
It's detected, actually, this is out of date. I forget how many, Chinkai probably knows. Almost 800 earthquakes around the world been detected by MyShake. Obviously very big ones, but also very small ones. Magnitude 1.7 earthquake. If you were sat on top of the epicenter, you would not feel that earthquake. But we've actually detected an earthquake as small as a magnitude 1.7 with the phones. I'm wrapping up here just to show you a couple of examples. This is our best example in terms of the number of phones that detected an earthquake. This was a magnitude 5.2 earthquake in June of 2016, so a few months after we rolled out. And the way this map works, so the earthquake is here, Borrego Springs. This, of course, is Southern California, so this is Los Angeles and San Diego here. The dots, all of the dots are phones that were running MyShake at the time of the earthquake. Okay? The red dots are the phones that were not in ready state, as in somebody was moving them around, so they weren't monitoring for earthquakes. The yellow dots were monitoring for earthquakes, but they did not trigger, so they didn't recognize that they were experiencing an earthquake. And then the green dots are the ones that did trigger, so they did recognize that they were experiencing an earthquake. And then sent a trigger message and uploaded data. So about 200 phones triggered for this earthquake. About 100 of them provided what we call good data. I mean, data that you could actually use, seismic data, that you could actually use to do an analysis of this event. Sort of to illustrate what that looks like, similar kind of thing. The blue dots are the phones that were running, and I'm just going to run this animation that shows how they trigger. And to guide your eye, you're going to see circles radiating out, just like that animation I showed you at the beginning, the P wave and the S wave, and you can see how they're triggering relative to the seismic waves as they radiate across the region. So the yellow is the P wave, and then the red is the S wave. I'll let it run again, but you could see as the energy radiates out, this is Palm Springs area, and you can see many of these phones trigger as the P wave comes across. So they're actually triggering on the P wave arrival, that first arriving energy, which is good. That gives us more time when it comes to doing the warning. Here we go again. So Palm Springs, and needless to say, as you get further out, the fraction of phones that actually recognize it's an earthquake shaking decreases. That's what you would expect, of course. And then the other example is, of course, this Berkeley earthquake, a little more detail now. So same kind of map in terms of the phones. So again, the piece that's amazing to me is that this is 2 years after we rolled it out. So this is pure citizen science. These folks have the app on their phone because they think this is an interesting citizen science project. I don't know how many dots there are on this map, but obviously several hundred, still running the app at this point. Again, the yellow ones, they were monitoring for earthquakes, but didn't trigger. The green ones did trigger. The earthquake is up here, so of course the ratio that trigger to don't trigger is much higher up in the Berkeley area. In this case, 59 phones triggered. 63 phones provided us with good waveforms. So that's telling us that not all of our triggers are actually getting to us on the real-time system. And then, so an animation, well, you've seen this animation, but I'm going to show you a different version of it in a second. So this is the one I already showed you. So 1 second, 2 seconds, you start to see the stations triggering, and then it's located in this simulation, offline version, of course, and it estimates a magnitude 4.9, which is pretty good for this particular earthquake. But what I want to show you is another one now where I overlay the P wave and the S wave from this particular earthquake. So that's the actual origin time. These are the P waves and the S waves radiating out. And then you can see the stations triggering in the location. You can see it's a pretty good location. So, here we go. So again, the origin time, energy gets to the surface after 2.5 seconds. The phones trigger after 4 seconds, and then the event is detected. So this is kind of our proof of concept event. We think that it's reasonable for us to say this can actually work and start providing alerts. And so that's actually what we're working towards as rapidly as we can at this point. Oh, I just want to mention, and then I'll finish, you can also use this to monitor buildings. I'm not going to really say much about this, but the sensitivity of the sensors is good enough to actually measure the fundamental periods of the building, so you can monitor how the buildings are shaking. And structural engineers are very interested in this in order to try and understand whether buildings were damaged in earthquakes by seeing changes in the characteristics of the buildings. So that's another avenue that's worth looking at. So to summarize the MyShake piece, we've had this roll out. The phones are actually doing much better at detecting earthquakes than we expected. So we're working very hard. The number one question we get is, when's the iPhone version coming out? So we're working very hard to put an iPhone version out later this year. And also we're working towards doing warnings. Interestingly, I think the first place we're going to start doing warnings is going to be in New Zealand. They really want this, and they're having a lot of earthquakes right now, so it's a good kind of match. And of course we're continuing, I haven't talked about it at all, but we're using the data for various research applications as well while this is going on. So the key challenges they're the same key challenges I think we've had in seismology for several decades. And it continues to be, first of all, this triggering on the earthquake. How do you really tell that you're seeing an earthquake just at an individual sensor? And separating it out from noise, obviously, particularly now that we're using these phones, and then associating these clusters of triggers. And it's the same challenge, whether we're talking about Shake Alert or MyShake, we still face the same challenge. That's the main source of errors, is that part of the system. In terms of the outlook for Shake Alert is pretty good. It's a proven technology. I think we will have a public warning system. The faces there are because this is really about the funding piece. And I was very careful how I chose the third picture. But I can tell you we went through a bit of a bump. The Trump budget cut Shake Alert out completely, but Congress is actually putting it back in. Of course, we don't have a final budget yet, but the budget legislation that is again on hold for another 2 weeks or whatever, as of noon today, actually has Shake Alert put back into it. So Trump's budget tried to take it out, but Congress has put it back in. And I think that's a really good measure of what we've been able to demonstrate to Congress about the capabilities of Shake Alert. And then MyShake, I think, is just getting started. I think it is a research project, but I really think it could have a global impact over the coming years. Okay, I'm going to stop there, and I'm happy to answer questions. And if they get too technical, I'm going to tell you to ask Chinkai. Thank you. Yeah.
Thank you very much. Very interesting talk. One thing I think you mentioned about how many events you'll be able to detect, but on the flip side, how many kind of false alarms has this algorithm created, or do you have any sense of that?
For MyShake? Right. So MyShake has created 0 false alarms. When we go back and we do this again, we haven't detected any events in real time either. Okay, but when we go back and we run the simulation through our simulated system, we should have detected. Most of them we didn't detect because we were not running the real-time detection algorithm, but we would have detected 4 events. So over the course of the 2 years that we've been running MyShake since the public release, we would have detected 4 events, we should have detected 4 events, and there would have been 0 false alerts.
What about for Shake Alert? The same question for Shake Alert.
Same question for Shake Alert. I actually don't know what the ratio is. There's many, many more real events than there are false events. We really worry about the false events, and so we're talking about 1Z, 2Z when it comes to false events. 1 or 2 events. Yes. I know it sounds like and I'm making an excuse, but it is really difficult to characterize exactly what you mean by false alert rate. Okay, so it depends on whether you mean the magnitude was off by more than half a magnitude unit, 1 magnitude unit, the location is off by more than 5 kilometers, 10 kilometers, or there's no earthquake whatsoever. Okay, now when you say no earthquake whatsoever, do you mean no earthquake anywhere on the globe? And the reason I say that is that the main source of false alerts for Shake Alert has actually been large teleseismic earthquakes, so magnitude 7 or 8 earthquakes on the other side of the globe that still trigger all of our stations. They actually have amplitudes that are not that different to some smaller earthquakes, when they're big earthquakes and they're deep earthquakes. So our problem in the past has actually been false alerts due to these teleseismic events. So you could call that there was no real earthquake, but you see my point. And I think we've had, I'm going to throw out a number, maybe 5 per year. with magnitude estimates of about 4. So you don't end up with really large magnitude errors, large magnitude estimates, but you end up with 4s. So you would push out the alerts for those. Yeah.
You've already sort of made your point that it doesn't matter if you get people warning when the shaking's already started or not, because there's bad things that can happen even after that started.
Right.
But I'm kind of curious about, you've said that the main thing you're taking advantage of is the distinction between the speed of sound and the speed of light. But transmitting an alert, say, through a network so far probably isn't really speed of light.
Right.
It's probably significantly slower.
That's right.
What is this? What are the relative ratios of the speeds?
Sure. So S waves, which carry most of the damage, travel at about 3.5 kilometers per second. Okay, so that's one estimate, that's one source of time delay until the actual shaking occurs. When it comes to the speed with which we can push out these warnings, we find, so there's the actual the processing of the seismic processing is negligible. The delays are that the traditional network typically sends 1 second packets of data. So you wait 1 second and then you send that chunk of data, you wait 1 second. So on average, that's a half-second delay, depending on where the arrival is, right, in that 1 second packet. The actual transmission time of that data, it varies from a few tenths of a second to a few seconds in some of the older stations, but an average might be about half a second. So a good typical time between when an event, a seismic arrival has hit a station and when our system can recognize it is about a second, let's say on average. Negligible time to process it, but then you have to push the warning out to people. We have far less data on how long that actually takes because we need to measure how long it takes for the thing to get to your phone or to your computer. But our best guesses at that is 1 to 2 seconds. To put that in context, everybody thinks about the Amber Alert system. Can't you push it out over the Amber Alert system, the WEIR system? That actually takes tens of seconds. So the current technology they use for that is not fast enough for earthquake warning. Yeah.
With respect to maybe just shake alerts, what would performance be for aftershocks, where perhaps rescue teams really can benefit from a pull away and then continuing with confidence?
Absolutely. So yes, and it's also the kind of situation where the tolerance for false alerts is also lower or higher, or it's better. You can looser. Thank you. But it's also a very challenging time in terms of seismic network detection because in an aftershock situation, you have many earthquakes occurring in very close succession. So the association part of the problem becomes much more challenging because you can have stations in different parts of the region triggering and you think they're coming from the same earthquake, but they're actually two separate aftershocks that are occurring just a few seconds apart in different locations. So, for example, Japan has a public early warning system that pushed out a warning successfully for the magnitude 9 Tohoku-oki earthquake in 2011. It was a big deal. But then in the aftershock period, in the sort of weeks, I think it was, afterwards, they had several incidents where they had magnitude 7 false alerts, which were due to the misassociation of arrivals from different triggers. So I would say that in that aftershock time period, I would agree with you entirely that that's a really good time for early warning because people are much more tolerant of these kind of false alerts, but you also get more false alerts as well. Yeah.
So it's a bit orthogonal, but are there technologies for tsunami formation and tsunami alert? I mean, does satellite data get used? I mean, I don't know if they can be detected at that resolution.
So the tsunami warnings that you hear about on the news are for warnings of tsunamis that are going across the entire ocean basin, across the Pacific Ocean. So then there's hours, right? So if we're worried about an earthquake in Japan causing a tsunami that affects California, we're talking about, I think it's 10 hours travel time. So there's lots of time to play with. If you want to worry about the tsunami, if there's an earthquake in Cascadia, offshore of Seattle, and you're worried about the effect of the tsunami up and down the Washington coast, there are almost no warning systems capable of doing that because there's no systems that can detect it quickly enough. The only way of doing it is to take Shake Alert and extend it. So what I haven't talked about here is that we have more sophisticated algorithms for larger magnitude earthquakes that actually not only estimate the origin point and time of the earthquake and its magnitude, they also estimate the total area of the fault that's ruptured. Now once you do that, so that takes a little more time, so it takes another 5 seconds, 10 seconds. But once you do that, you can use that to predict what you might expect for a tsunami if it's a subduction zone earthquake. And so we find that you would be able to provide information about a tsunami in about a minute. And it typically takes 5 to 10 minutes for the tsunami wave from, in the case of Seattle, for an earthquake offshore of Seattle to hit the coast. So there's actually real value to extending what is earthquake warnings in order to do the tsunami warnings. I flippantly tell people that if you do earthquake early warning, you get tsunami warning for free. Yeah.
How much do you think having the network buys you versus just having a localized alert from your phone?
You mean, or not even a phone, if you just have a sensor, and that sensor sees something and it sounds an alert. Yeah. So it has the advantage of simplicity. Clearly, that's a big deal. But of course, the sensor, so now the question is, are you going to try and detect the P wave and issue a warning before the S wave? Or are you just going to wait for there to be significant shaking and then sound an alarm? And so if you wait for significant shaking and sound the alarm, well, the person probably felt that shaking as well. There still is some value to that, to be clear, because what people who study these things have seen very clearly is people start to feel shaking and we all look at one another. Is that an earthquake? Do you feel that? I'm not sure. What should I do? Do we know what to do? Now, if an alarm goes off and it says earthquake, and you know when I hear that alarm, I get down between these chairs. So there's value to that. But it's difficult to imagine a scenario where you get warning before you start to feel the shaking yourself. So that limits the value, I guess. Yeah.
So you're focused on damage, danger to persons and property, and absolutely correctly, of course. But my recollection from the Loma Prieta earthquake and its aftershocks was that it was the aftershocks, not the initial earthquake, that were psychologically wearing on me and the people around me. Going on for weeks and weeks. These magnitude 5. Have you considered, especially with respect to aftershocks, whether people are going to be more or less psychologically affected by receiving a warning or not?
There have been no studies of that. But I would agree with you. Obviously I'm an advocate for earthquake early warning. I feel like I'm sometimes doing a battle with colleagues, my seismology colleagues, who get incredibly focused on we can't have any false alerts, and the accuracy of the information we provide has to be perfect. And what about the aftershock problem? People are really concerned about false alerts for aftershocks. And I would argue, which is exactly to your point, that for people who are experiencing the earthquake, and we've seen, and I'm not just making this up, this is again what we've learned from Mexico and also from New Zealand. To your aftershock point, when people have just had a big earthquake, there's a complete feeling of helplessness. That this thing that we consider to be rigid and fixed, it's not. It could all collapse, kind of thing. And so having a warning system provides some sense that we're doing something about it, even if that actual warning system may not be performing particularly well. I think that's what we heard in the commentary we got from the public that we interviewed after the Mexico earthquake. So I would put that into what I think of as being kind of the broader benefits of earthquake early warning, are helping people through what is a very traumatic situation, are helping people to think about the earthquake before it happens, increase the rates with which people prepare for earthquakes. And so those are the sort of, we're increasing, one of my social science colleagues calls this the seismic culture. We're enhancing the seismic culture by which people are aware of the problem and they understand what they can do in order to reduce the impacts, and they actually take actions as opposed to just being, I'm just not going to think about it.
So in order to have a break, could we have the rest of the questions?
Good point. Absolutely. Yes, okay, so I'm happy to keep answering questions out the back. I'm afraid I can't stay for the rest of the afternoon. Chinkai can answer questions as well later this afternoon.